And now we have time for open discussion, general discussion about these things. And maybe I can start with something very general here, since we'll be talking about Sagittarius A flares and variability of Sagittarius. I was wondering, what everybody thinks. Can we actually expect that some of this variability is due to this kind of processes that Alex just described, some kind of particle acceleration in the charge gaps in a black hole magnetosphere? Maybe flares, or maybe just variability. And then, if we expect this to happen in Sagittarius, then wouldn't we expect us to see the same thing in M87? And do we see these flares in M87? So,
Well, yeah, with M87, there's that related concern about when you're modeling the spectrum, are you just modeling a random sampled time that would, like in Sagittarius A star, would show up as this much more variable emission that you wouldn't necessarily try to model the spectra and like fit the data points. Sorry. But like in M87, you have, because the time scale is so much longer for things to change, are we just looking at the higher frequency emission? Is that just Sagittarius A star like variability that we're not seeing evolve?
Yeah, how high frequencies are you talking about?
Sorry, coughing fit.
Just very simply, Alex, how do the energies, like the voltage drops, scale between M87 and Sag A star?
Yeah.
Let me check.
Yeah, I think for the M87 models, the electron Lorentz factors are very large, right? When the cooling of these, in your model, right, Alex, when the cooling of these electrons balances their heating, the limiting Lorentz factor is, I don't know what, 10 to the 6, 10 to the 7?
10 to the 8, several times 10 to the 8.
This would be very large compared to what we nominally associate with Sag star flaring, but it presumably does scale, and it's a very interesting question.
Also,
I think this was the point, that in M87 you don't really expect radiation at similar frequencies from this, right? It's a very high energy emission process for this reason.
Yeah, that's true. But also for Sagittarius A star, it's complicated because according to our model, it's marginally, like, even if you have a gap, the optical depth is so low that it may not be even able to produce enough pairs to screen itself. So there's actually possible different kind of kinetic physics there that could happen. Maybe like the 2D GRP people that can actually simulate this regime, and that could actually be more applicable to Sag A star.
I was wondering, actually, let's assume that Event Horizon Telescope will measure the spin of Sagittarius A star, and it will turn out that it's 0. Would that kill all the gap models?
Yep, maybe, yeah.
But in your model, Alex, when do you have a spin as a parameter of rotation, or it must enter the model somehow, right?
It comes in implicitly. We have assumed a rotation angular velocity, and so we basically took A equal to 1. No, I think it's 0.99, but it's, yeah. But yeah, we have an implicit assumption of the omega. But in that case, and also because everything scales as jet power, so yeah, there's also spin comes in there.
It might be a related point, but the work on tilted disks and feeding from stellar winds, would suggest that the funnel could actually look quite different in that case, right? Like, it's actually, does it become mass loaded, or what is actually is it still set by floors in those calculations? Or Chris or Sean?
Yeah, I can say, I can't tell you in the actual full calculation of like the stellar wind feeding GRMHD. I have a simplified version, which is just you assume there's no angular momentum and you just run a GRMHD simulation like that. And even then, as long as you have good amount of spin. I'm only doing 0.93, the normal 0.9375 that everybody uses. But using that spin, you still get these very evacuated jets. But the thing is, they will like disappear and reappear. So they're continually fighting against the stuff that's falling in. And they're much slower because they have to continually push against them. And they get disrupted by like kink instabilities. But overall, they're still completely evacuated.
Though I think, Sean, if I remember when I looked at some of them, like they're different. Even when they're there, they're narrower.
Yes, they're very narrow.
Like the jets just look different in that case. And in the tilted disks too, there's definitely just all sorts of mass in what used to be a large vacuum region. I don't know. I haven't looked specifically at the jets there, but I don't think, I wouldn't be surprised if there's differences.
And is that, I mean, I don't know if you know, is that real mass loading, or is that floor stuff, or is that real mass loading?
It's way above the floors.
Yeah.
So in your simulation, Sean, how often is the disk co-rotating with the black hole and counter-rotating?
Okay, so...
Because I guess that would be also another way to go, to actually look at the mass loading or pair production in those models where there's a misalignment between, like complete misalignment, between the disk and the black hole spin.
So unfortunately, I cannot answer that question at all, because in the realistic simulation that I have, it's 0 spin. And in the unrealistic the less realistic simulation I have, it's 0 angular momentum. So I have the two extremes. I can say that what I did vary in the 0 angular momentum case is the magnetic field direction. So just assuming a uniform magnetic field being advected inwards, if you vary the magnetic field direction, the jet is still always pointed in the direction of the spin of the black hole. There's some tilt that can develop, but it's more random. It's not really dependent on the magnetic field direction. So in a torus simulation, that would be like somehow varying the geometry of the magnetic field, so that's not really aligned with the torus completely. But I'm definitely looking into the more realistic case of actually putting in spin, and then you have the angular momentum direction of the stuff being fed by the stellar winds. Then you can compare that to the spin of the black hole. And so that's coming sometime in the future.
Yeah, we're looking forward to see your new models. Does anybody else has thoughts on this? I was actually also wondering in terms of, charge gaps and so on, and M87 again, going back to M87. Because, Event Horizon Telescope has imaged the source, and we have some estimates for the magnetic field strength in the source, and it's, of the order of just a few Gauss on the ring that we see. That's our constraint. And I was wondering if those gap models would, if this is what we see actually, how would they look like in EHC observations? Because, from Alex's simulation, I presume they would be formed very close to the black hole. And would that change our, some constraint on the magnetic field strength in the source, for example?
Yeah, so there are quite several things here. It looks like the magnetic field from EHT modeling is really low. And we have, in a lot of these models, we assumed pretty high magnetic field. I mean, high.
I saw something 10 to the 7 Gauss, or was
that?
No?
No, it's not. But that's the numerical value, not.
Not in SI or CGS. Okay.
So we assume 200 Gauss, which is still very high. So if B field is much lower, then the gap power will be lower. So it looks like the gap power is rather low, given the optical depth as well as the magnetic field. So it's nothing like what the TeV magic they saw 10 to the 41 ergs per second. It's nothing close. It's about two orders of magnitude lower than that. And regarding what we see from EHT, that probably relates to my comment on multiplicity, because we essentially see the electrons around the horizon, and the electrons produced in the gap are very, first they're high energy, also they have very low number densities. So we probably don't see this component produced by the gap itself. It will be very, very hard to see from all those things produced around it from the accretion disk. But maybe like the hope, maybe is there a way to combine other wavelengths and with the EHT and maybe independently modeling, because one of the things I was talking about was long-term variability. It's not that long-term. The simulations have run like several thousand RG/C, right? A couple of years is just several hundred RG/C. So in the simulation time, this is not that long-term variability. So in several hundred RG/C, you have this very big changes, order of magnitude changes in the TeV flux. What could cause it? Do any of you have any ideas?
I would love to hear from the participants of the conference more. Anybody has a comment on this or idea? Yeah, I guess, Alex, nobody has ideas yet how TeV flares are formed. All right. Are there any other topics that would be interesting to discuss today? I can see something in the chat. Okay. I think people just slowly signing off from the meeting. So I would suggest to close the meeting now. I would like to thank everyone for participation and for your comments and your contributions to discussions. And I would like to, again, thank all the speakers for wonderful talks. Thank you very much.
And also